Hello, everyone. Today I'm going to talk about the optimization of refueling strategies for space missions. This work was presented at the American Institute of Aeronautics and Astronautics SciTech Forum in 2025. I will start by giving a quick motivation for this work. So, the current space industry architecture is based on single-use systems, where each spacecraft is designed as a disposable unit. In this architecture, the main lifetime limiting factor is the propellant capacity of the spacecraft. This causes high launch mass and costs because the spacecraft must carry all the required propellant from the ground. This also reduces the flexibility and adaptability of the mission. The alternative space industry architecture is based on refueling. Refueling allows for smaller spacecraft and cheaper launch vehicles. It also allows to adjust the trajectories and repurpose the missions after the launch. It also reduces the environmental and economic impact. And in order to achieve in-space refueling, many research areas have to work in synergy, like orbit design, autonomous robotics, fluid dynamics, etc. In this work, we focus on the propulsion system and particularly on the electric propulsion systems. And the goal is to define the performance metrics for refueling, starting from the first principal equations of propulsion. Now, I'm going to present the Stallinger theory from the 60s, which is for the case of no refueling. Stallinger was a German-American rocket scientist, and he wrote several seminal papers on propulsion. And in this paper from 1967, he introduced a quantity called the normalized payload and structure mass. It is defined as the mass of the payload plus the mass of the structure of the spacecraft, normalized by the total mass of the spacecraft. Then, using these underlying equations, he was able to derive an expression for this quantity. So he used the mass budget of the spacecraft. So M0 is the total mass, MPS is the mass of the power system, MP is the mass of the propellant, MS is the mass of the structure, and MP is the payload mass. In addition, he used the rocket equation and an expression for the input power, and he assumed a constant mass flow rate m dot. So this assumption allows us to write m dot equal to the total mass of the propellant divided by the firing time of the thruster. And using these equations, we can show that the normalized payload and structure mass can be written in terms of the exhaust velocity, c, the delta v, which is the required change of velocity of the mission, and interaction of the characteristic velocity that is also called the Stallinger velocity. And this velocity represents the theoretical upper limit velocity that an electric thruster can achieve. It is a function of eta, which is the power efficiency, and alpha, which is the specific mass of the power system. For example, if we have a solar array, the specific mass of the solar array is the uh, mass of the solar array over the power that it can produce. And TF is the firing time of the thruster. And we can also define these normalized quantities, delta V bar, which is uh, the required change of velocity, delta V, normalized by the Stallinger velocity. And we can define the normalized specific impulse, which is the exhaust velocity c normalized by the Stallinger velocity, and then we can rewrite the quantity h as a function of these normalized quantities. And the description of delta v and the specific impulse was given in a previous video. So then we can plot the quantity h as a function of the specific impulse c bar for different values of delta v bar between 0.1 and 0.8. And we see that for a value of 0.8, the normalized payload mass is negative, which means that the mission is not feasible. So the main result from the Salinger theory is that the maximum delta V, for which a positive payload mass can be carried, is equal to 0.8 the characteristic velocity of Salinger. So only missions with lower delta V can be achieved with electric propulsion. Now, I'm going to introduce uh, some performance metrics that we defined for a mission with refueling. And for this, we started with the Salinger theory and tried to generalize the theory to include refueling. So let's consider a mission that goes from an initial orbit, R0, to a final orbit, Rn. And along the mission, we have n minus 1 refueling stations, and therefore we can divide the mission into n segments. If the total requirement of the mission is delta V, then we need to achieve a fraction of this total delta V at each segment. So the sum of all the fractions of delta V from 1 to n has to be equal to delta V. And therefore, the sum of the coefficients beta I is equal to 1. And for the specific case of a mission without refueling, we only have one segment, and therefore n is 1 and beta is 1. Next, we reproduce the same methodology used by Stallinger, but we apply it piecewise for each segment. So we apply a piecewise mass budget, where MPI here is the mass of the propellant required to achieve the segment I, and MPI is the payload mass that could be transported during the segment I. Then we apply a piecewise rocket equation, and we can get MPI, which is the propellant required for each segment. And then the total mass of propellant MP star is just the sum of MPIs from 1 to n. And we note that the sum of the mass of the propellant at each segment is larger than that of emission without refueling. So the sum is higher than the initial value of the propellant mass. And this can be understood by seeing this figure here. So in the yellow case, we have no refueling. So the mass of the spacecraft just decreases with time uh, since the propellant is consumed. However, for the case of refueling, at each refueling station, we have some additional mass of propellant, and therefore the average mass that is transported over the mission when we have refueling is higher than the average mass when we don't have refueling, and therefore we need more energy, and therefore the mass of the propellant is higher overall. So this is the first result from these equations, which is that the total propellant mass over all the mission segments is larger than that of a mission without refueling. Next, we can derive an expression for the normalized payload and structure mass, and we have a value for each segment. So this is a function of beta I, which is the coefficient of the fraction at each segment. So the payload mass is different between the different segments. However, the actual payload mass of all the mission has to be equal to the minimum one of all the HIs. Because the same payload mass has to be transported from R0 to Rn. So the minimum payload mass is the overall payload of the mission. And this is achieved for the maximum value of beta, which means that the overall normalized payload mass of the entire mission is constrained and defined by the longest segment of the mission. This is because the longest segment is the one that consumes the most propellant. We can also show that the sequence of beta the optimal one is when all of the betas are equal and equal to 1 over n. So H star, the overall normalized payload and structure mass, is maximized if all the betas are equal. So have the payload mass is maximized when the distribution of beta is uniform. So having a uniform distribution of refueling maximizes the normalized payload mass of the mission. And we can also show that this quantity increases with n, so the derivative with respect to n is positive, and therefore the payload mass is a monotonically increasing function of the number of refueling stations. Then we can generate this plot of the normalized payload mass as a function of the specific impulse. And we do it for the extreme case of delta V over the characteristic velocity equal to 0.8. And as we showed earlier, the payload mass is negative and therefore the mission is not feasible. However, if we increase the number of segments in the mission, which means if we do refueling, then the payload mass becomes positive. So the mission is enabled if refueling is used in the mission. And we can also see that the distance between the different curves decreases as n increases, which means that the benefit of refueling diminishes when we have a higher number of refueling stations. Then we can plot the optimal C-bar that maximizes these curves. And in this case, we can ignore the first value because it corresponds to a negative payload mass. And we can consider the second value to the last one. And we see a decrease in the optimal normalized specific impulse when the number of segments increases. And the specific impulse represents the mass efficiency of the thruster. And since it decreases, this means that the mass efficiency of the thruster is less important if refueling is available. We can also show that there is an upper limit of H star by taking the limit of n to infinity. And we can show that this is the maximum value of the normalized payload mass. And we can take some values for delta V bar and C bar to show this plot here. So this is the mass fraction of the spacecraft as a function of the number of segments in the mission. And there is a constant fraction that is dedicated to the power system in the spacecraft. And then when we have more refueling, the propellant that the spacecraft should carry decreases here in green. And this gain in mass could be used for the payload mass, which then increases here in blue. And this increase converges to this maximum value, H infinity. And so we can see that more refueling stations is not beneficial after a certain threshold when we get closer to the limit. We also define another performance metric based on time considerations. So for low thrust maneuvers using electric propulsion, the total mission time can be approximated by the firing time because the firing is continuous over the mission. And if we assume a constant mass flow rate, m dot, for the case of refueling and the case of no refueling, we can show that this ratio, the firing time ratio, which is the firing time with refueling over the firing time without refueling, we can show that this quantity is always greater or equal to 1, which means that missions with refueling are always longer than missions without refueling. And we can show that this quantity, tau, is minimized if we don't have any refueling, so we only have one value of beta, and it is maximized if refueling is uniform. However, in this case, the goal is to minimize the time. So we get to two extreme cases. In the first case, we want to maximize the payload mass in which case we want to have many refueling stations. And in the second case, we want to minimize the mission time, in which case we want to avoid refueling. And in actuality, in a real mission, if both considerations are important, if we want to both maximize the payload mass and minimize the mission time, then the optimal strategy should lie somewhere between these two extreme edges. And then we define a third performance metric, which is the specific propellant consumption, which is defined as the total propellant mass over the payload and structure mass. And you can also show that this quantity depends on the normalized specific impulse. And we can also show that this quantity decreases with increasing number of refueling. Yeah, so the specific propellant consumption decreases with the refueling. Next, we are going to apply our framework to an actual mission. And for this, we chose the Smart One mission. Smart One was an ESA mission launched in 2003. And after an insertion into a geostationary transfer orbit, it used its Hall effect thruster to achieve lunar orbit, and it followed an elliptical spiral orbit. From the literature, we have these reported values. So we have the mass budget of the mission. We have the power, the specific impulse, the thrust, the delta V, the mission time, and the firing time. And using these values, we can calculate the corresponding performance metrics in addition to the jet power and the power efficiency and the specific mass, etc. Then we define this optimization under constraints for problem. That is, for given values of delta V normalized by the characteristic velocity and the specific impulse normalized by the characteristic velocity, find the refueling sequence beta I between 1 and n that maximizes the normalized payload and structure mass, and the following constraints. The first constraint is that all the coefficients must be between 0 and 1, and the sum of the coefficients must be equal to 1. And n, the number of mission segments, should be smaller than some n max that we can prescribe. And tau, which is the firing time ratio, should be smaller than some tau max that we can also prescribe. And then we use numerical methods to calculate the optimization of the problem. So this problem is non-convex, which means that it has many local minima. And for this, we need to use a local optimizer. In this case, we use the sequential least squares programming, SLSQP. And this local optimizer can only find the local minima. So we need a global optimizer. In this case, we use the basin hopping algorithm. So this algorithm jumps or hops between the basins. So it jumps from all the local minima, and then it gives you the minimum of all the minima. So we use these two optimizers in order to calculate our optimization problem. And so we define 4 cases. In all cases, we prescribe nmax to be equal to 10, which is the maximum number of mission segments. And then we have different values of tau max. In the case 1, tau max is just 1, which means that we don't want the mission to be longer than the actual Smart 1 mission. In case 2, it is 1.02, which means that we can tolerate up to 2% longer missions. In case 3, 1.08. And in case 4, there is no constraint on the time, which means that the mission can be as long as possible. And here are the results. So for the first case, the result is just having one segment where we achieve 100% of the total delta V, which is the actual Smart 1 mission. In case 2, we have 2 segments. In case 3, we have 3 segments. And in case 4, we have 10 segments. So when we don't have any constraint on time, we have a uniform distribution of refuelings. And here are the performance metrics. So H is the normalized payload and structure mass, F is the specific propellant consumption, and tau is the firing time ratio. And we can, for example, compare the first case with the last case. And we can see that there is an increase in the normalized payload and structure mass of 20%. So 20% of the mass of the spacecraft can be dedicated to having an additional payload mass if we have refueling. At the same time, there is a decrease in the specific propellant consumption of 9%, which means that even though we could use more propellant, but the propellant over the payload mass ratio is decreased. And this comes at the cost of having a mission that is 10% longer than the actual Smart 1 mission. We also notice that H10, which is the normalized payload mass when we have 10 segments, is 97% of H infinity. So this means that having more refueling stations is not beneficial. So for conclusions, we have shown that in-space refueling enables missions with higher delta V, higher payload mass, and lower specific propellant consumption. We have also shown that the mass efficiency of the thruster becomes less important if refueling is available. We also showed that the payload mass is maximized when refueling is evenly distributed over the mission, and that there is a theoretical upper limit of the potential benefit of refueling, and also that the gain in the performance metrics comes at the expense of a slightly longer mission time. Finally, this analysis assumes no time penalty and no delta V penalty for rendezvous with refueling hubs, and this should be considered in future work. With this, thank you for listening.